kidding. Okay, so we talked about Riemann sums, and we're going to compare Riemann sums. So that notation, we just loved this, and we would write what over here? So we wrote limit as delta x approaches 0, and we want infinitely many subintervals for an accurate answer here.
One more. Should we turn that in, or?
Just said that.
Oh,
but yes,
sorry.
it's all good. Okay, so here we are, sigma just means to sum up. So we're summing up a whole bunch of little rectangles here. We put that through the limiting process. You guys loved it. We looked at, or we talked about how we want to think of this as f of x times delta x, where f of x is the height of your rectangle and delta x is the width or the base of your rectangle. So multiplying that gives you the area of 1. Now, this idea is actually equivalent to what we're doing with our integrand. So our integrand from a to b of f of x dx is simply another notation for this. So thinking about sigma, what kind of letter is that?
It's a Greek one.
It's a Greek one. So
Almost a backwards E.
this is the land of the Greeks, not the geeks, the Greeks. This is a love it. This is the land of the Romans. Okay, so this is actually the integrand. That is a Roman S. So again, for summation. So this is summation for Greeks. This is summation for Romans. So I don't want you to feel like when you're looking at this notation, we're doing something completely different than this. This is just a different notation, but just to make it abundantly clear, same thing, different notation.
I like Roman.
That's awesome.
Same.
Yeah, it's so much easier to write.
Okay.
S than the...
Yeah. So if you if you like the Greeks, I'm sorry, you get to do it sometimes, but not all the time. All right. So what we've been doing, we started off with a geometric approach here.
Like whenever they were in historically, were they just always rivaling each other and just trying to?
I mean, I guess you could say that was happening with a lot of civilizations throughout time, but yes. All right. We said that we need to find the area under a curve, under a function, and sometimes we can't just take a geometric approach. So obviously the problem with something like this is I can't just break this into a triangle plus a rectangle and get the exact area under the curve. So that's why we need calculus, to allow us to solve for the exact area under here without having to use that crazy limit process and using our summation formulas to make it happen. So let's say we're solving from A to B. Because I don't want necessarily the total area under the curve forever. I just want a part of it. So color coding a little bit here. You don't have to. I like to color code. So in this region, I would be finding only the area between A and B, and that's what we used our fundamental theorem of calculus for. I'm only finding the area between two specific regions, so on a closed interval. So we're going to write some formulas today, and really want you to think of these as properties. So we are covering today the properties for working with area under the curve, working with the definite integral. Definite integral versus indefinite. You know the difference when I say definite versus indefinite. Honest.
No, not really.
Okay. One is a set boundaries. One of them we have from A to B. We are finding area of a set, a definite, if you will, region. We're finding the area under a definite closed interval. So we're finding area between curve and x-axis of a specific region. The indefinite integral is when I just give you a function and say, integrate this, and then you do the whole plus C business. You're writing a general rule for finding area under the curve, but you're not calculating area over any specific region. You're just look at it like you're creating an area function. So what we're doing here is we're actually going to evaluate over specific closed intervals. That's what makes it definite. Definite integral, you're going to have boundaries A and B. Indefinite integral, these will be absent. You will simply have an integrand sign, and you will find the antiderivative of a function, and that's when we need our plus C, our constant of integration. So for our first rule, or first property, if I have an integral from A to B of f of x plus or minus g of x, right, dx here, so that's our, that's what we're going to integrate with respect to, so x. This is equivalent, and we've essentially already done this. The first property says that there's no problem taking these two terms and splitting them up and giving each one of them their own integrand and evaluating them individually, and then just adding or subtracting their values. Okay, so if it feels more comfortable to split them up and take the antiderivative of each individual term, go for it. So that's property number 1. Property number 2, again, review. If we have an integral from A to B, so our closed interval, so this is a definite, and we have some constant multiplied times our variable or times our function, what can I do with K?
Bring it
Put it
outside.
in front.
Love it. Bring it outside. Put them in front of f of x dx. So just knowing that this is an option for you, a lot of times these antiderivatives can be a little bit of a headache. So bringing that k out, bringing that constant in front, gives you something simpler to look at. Our brains tend to do a little better with that. All right, now this one, I want us to figure out what that one is. What would that be equal to? So from A to A.
I can't tell that's what that says.
So from A to A, it would be equal to, so if I asked you to find the area,
Is it 1 point?
yeah, find the area under the curve, starting at A and ending at A.
0. It's 0, because there's no difference.
Okay, cool.
Y'all are smart.
No width, no area. All right, number 4.
They should not say bandwidth.
Number 4, I'm putting B on the bottom and A on the top. B on the bottom, A on the top. This is a brilliant group of people. So put B on the bottom, A on the top of f of x dx. This will be equal to negative, and then make it right from A to B. Okay? So if your integrand is set up backwards, what we're doing is we're measuring the area in reverse. And we will get into this a lot more heavily when we come back in January. But there is, the direction matters. So if you're measuring B to A instead of A to B, we want to know that it's okay to go ahead and change it back to what it normally would be, but we need to realize that when you're going the wrong direction, that's going to make your area the opposite sign of what it should have been. So
Negative area, though.
because, and I'm getting a little ahead here, but just like we have negative, velocities, and it just means it's a directed, it's a directed speed. Look at it like that. Area can be positive and negative in this world, and it's just a matter of direction. So if it's above the x-axis, you have positive area. If the area or the curve is beneath the x-axis, you have a negative area. It would be underneath the curve, but we're going to focus on that a whole lot more.
If you were like,
Actually have a negative area.
in the real
Well,
world,
like,
it
if
would
it
be
was
like if you dug a hole somewhere and you were trying to measure the. So it's like the absence of space.
Yes, yes.
See, so it is like depth.
Yes, that's one way to think of it. There are other applications of it where I don't want to get off on that because that's a whole realm, okay, of this. So I absolutely am with you as far as why you'd be thinking of that, but let's save that for another day. Today, my goal is that we feel okay about using our properties. This is the fifth and final. This is it. There are only 5. There will never be more than 5. If there are more than 5, you are making them up. So you do not need to be creative here. You have 5 properties. Your last one says that if you have an integral from a to b, so from a to b,
That must be something crazy.
of f of x dx plus, let's say you have a whole nother integral, but this time we're going to go from b to c.
Oh no.
What? Of f of x dx. Can't we just say that this is the same
See? Okay.
as a to c?
Yes.
Okay, so these are pretty brain friendly.
Boom.
Yeah.
All right. And so this would just be like going back to our picture here. If we picked a point C, and let's just say I started with my area of A to B. Let's say I already had that answer. And then another point in the problem, I want to calculate from B to C. I know that it would be okay to simply think of this as from A to C. So A plus B's area, or A to B rather, plus B to C should be equivalent to A to C. And then please write yourself this friendly reminder that these are your only, I should say there are only 5 properties. Don't make up your own. Okay? As gifted as we are, I don't want you making up your own. So I want you to stick to these 5. There are no more.
What
What if
if
we
we did
did-
one of the
What
works?
if we found
Then I can't wait to brag and say that I taught a student that added another property of antiderivatives.
Lucas, go.
Get on it, Lucas.